Hi there! In this video, I will show you how to debug your ESP32 IDF application inside Visual Studio Code. We go through the steps to set up and configure an external debugger and how to make it work reliably. Let's get started. Hi, I'm Yuri, and this is my second video of my ESP32 series. In my last one, we have learned how to use the ESP-IDF framework on Visual Studio Code. By the way, thanks to everyone who watched and for all the positive feedback, I really appreciate it. Today, you are going to learn how to debug your ESP-IDF application. Debugging is an essential skill for any professional firmware developer. It allows us to find problems and have an insight of what's happening during and after code execution. There are many different methods of debugging a microcontroller. Let's first take a look in the most common and simple one, which is using the serial terminal. Basically, this method involves adding the debug message that will be displayed in the terminal. This is the most simple way to gather information about the execution of our code, and it's useful if you don't have an external debugger tool. The ESP-IDF has a wonderful capability of catching exceptions and misconfigurations, and integrates itself with Visual Studio Code without any extra line of code. Let's take a quick look on how that works. Through the idf.py monitor command, we can see on the terminal some information regarding the ESP32's initialization and partitions. Also, when there is an exception, the serial terminal shows a very complete report with the reason, the line where the problem happened, and even the call stack with a history of our function calls. For example, here, this bug was a division by 0 on line 44 of my blink.c file. By holding the Ctrl key and clicking on the printed line, we can make Visual Studio Code jump to the line where the exception happened. As you can see, this method is pretty straightforward. However, it has some limitations. For example, what if you cannot use prints at all, like inside of interruption callback? How do we get any information? For that, it's better to use an external tool. External debugging devices use a common debug interface to communicate with the microcontroller. And trust me, they are extremely useful for developing. There are many different debugging interfaces in the industry, such as SWD, ICE, and JTAG. Today, we are going to work with JTAG since it's natively supported by the ESP32 and it's very popular. And here are some cool things that you can do with a debugger. We can define the so-called breakpoints, which will stop the execution of our code when it reaches that point. We can manually control the execution of our code by stepping in, out, and over functions. We have access to a variable list, where you can see the values for all variables and pointers at that time. We can even set a conditional breakpoint, which will stop the code if only a certain value is true, like a variable reaching a certain value, for example. And one of the most useful features, the trace breakpoint trap, which will automatically force a breakpoint when a crash occurs, giving us a lot of useful information. So in the next steps, I will show you which debugger to buy, how to connect your debugger, how to configure OpenOCD, how to configure GDB, and how to configure Visual Studio Code. So, which debugger tool should I get? Where can I get one? There are many different debugging tools in the market. Expensive and powerful ones, such as this Sega J-Link Pro, which is aimed more toward professional applications. And also simpler and cheaper ones, like these guys, using the FTDI 22328 chip. This is a high-speed USB to JTAG IC that provides the debug interface for us. You can buy a debugger with this chip for less than $25 on the internet. There are many different board versions available, but to get started, I highly recommend getting this one called ESP-PROG. I will leave the links in the description below. Alright, let's set up our debugger. Today I'm going to show the connections for the ESP-PROG, since it's easy to buy one and it's the official debugger from Espressif. It doesn't matter which device you use in the end, as long as it supports JTAG, the pin connection for the interface should be the same. The connection with our PC looks like this. The ESP32 is connected to the JTAG debugger through the I/O pins. The debugger is then connected to our computer using a USB port. This port is controlled by the JTAG Windows driver. This JTAG connection is then managed by a background software called OpenOCD, and then controlled by Visual Studio Code through another software called GDB Debugger. And we also connect our ESP32 to the computer, using a second USB port so we can use the serial monitor. Don't worry, I will explain each of these steps in more detail in a few minutes. The first step is to connect it to the ESP32. The ESP-PROG has two connectors. This first one is used for the JTAG, and the second one for the serial interface. Both can be connected to the ESP32 and used through just one USB cable. But in our example, we are going to connect just the JTAG and use the serial through the ESP32's USB interface, to keep it simple. For the ESP-PROG, we should connect it like this. Connect ground to ground, 3v3 to 3v3, TCK to IO13, TDI to IO12, TDO to IO15, and TMS to IO14. In case you have a generic FTDI breakout board like these ones, the connection should be like this. After that, we'll need to connect the ESP32 and the debugger to our PC, using two different USB ports, one for the ESP32 serial interface and the other one for the debugger's JTAG interface. But first, in order for Windows to properly recognize the debugger tool and work as a JTAG interface, we need to install its driver. In our case, the FTDI2232H USB JTAG driver. Let's take a look. Since the Windows libraries already have a generic version of this FTDI driver with only the UART interface enabled, we have to update it to add support for the JTAG interface. We are going to use a driver updater called ZDIG. You can download it through their official website. Let's open it, go to Options, and then select List All Devices. Then, select Dual RS-232 Interface 0 and click on Replace Driver. This will update the driver for the FTDI, giving us the ability to use the JTAG interface on the FT2232H chip. To refresh the driver connection, unplug and plug the USB back in the computer. Keep in mind that if you plug it in a different USB port, you might need to install the driver again. Now that we have all the physical connections ready, the next step is connecting the JTAG to OpenOCD. OpenOCD stands for Open On-Chip Debugger and is responsible for managing the communication with the debugger driver, in our case, the FTDI driver. Let's open a new terminal on Visual Studio Code. Make sure your environment is already configured for the ESP-IDF. If you don't know how to do this, check my previous video here. By the way, as many of you pointed out in my last video, Visual Studio had an update and now we need to configure the IDF terminal in a different way. I will leave a link with the new instructions in the description. In this example, we are going to use the same Blink project as before, to keep things simple. In the new terminal, type the following command: OpenOCD-F board/ESP32 rover kit 3.3v.config. This configuration file depends on the ESP32 module being used. You may need to provide a different file if you use a different one. You can find more details on the IDF documentation. If you have connected your ESP32 properly and your driver is installed correctly, you should see this output. This means our debugger is wired properly and is up and running. By the way, in case your debugger is not connected properly, you may see something like this. And if your driver is not correct, you may see something like this. The next step is configuring GDB inside Visual Studio Code. GDB is the GNU Debugger, an open source debugging software used by Visual Studio Code to communicate with OpenOCD. To do this, let's click on the Debug button on the VS Code menu and click on Run and Debug, and then on the C++ GDB option. This will create a file called launch.json inside of the .vs code directory in our project, which we will use to set the debugger parameters. Let's start by removing these lines that we are not going to need. Now, let's add the parameters that we are going to use. Name, which is how you call this debug configuration. Type, which is the debug type, in our case, CPP-DBG. request, which is launch, CWD, which is your workspace/build, program, which is your ELF file, in our case, workspace/build/blink.elf, me debugger path, which is the path where your ESP32 GDB executable is. If you have followed my previous video, you should have a folder structure similar to this one. Don't forget to correct the backslashes to forward slashes, otherwise it's not going to work. Setup commands. This is a list of GDB commands that will be executed by the debugger at startup. The first command is going to tell GDB how the connection to OpenOCD is going to be established, in this case, through localhost and the default port. The next command specifies how many hardware breakpoints this microcontroller supports. Checking the IDF documentation, we know the ESP32 supports only 2. The next command is monitor reset halt. That command resets the ESP32 and keeps it halted. And finally, flush reds. This command forces GDB to flush its internal register cache. And now, let's save the file. Before we move on to the next configuration steps, we can give a quick test to our debugger for the first time. We first need to make sure that we have loaded the latest firmware build in our ESP32, and also that OpenOCD is running a terminal connected to our board. Finally, we can try debugging by clicking on the debug icon, and then on the play button next to the ESP32 OpenOCD. If everything was set up correctly, the debug buttons will show up on the top. Now we can add breakpoints and play with all those functionalities that we've seen in the beginning of this video. However, since we need to be opening OpenOCD manually all the time and also loading the firmware before we start debugging, would be really nice if you could automate everything in order to make our life easier. This is a very important step that I highly recommend you to do. Let's do this now. First, let's make OpenOCD run automatically when we start debugging. Let's create a file called task.json inside of that .vs code folder. To do this, go to Terminal, Configure Tasks, and C++ build active file. Let's delete those lines. Now, let's write the properties for this new task. Start with label, which is the name of this task, then the type, which is shell. As you are running in Windows, we have to describe the command in Windows session, like this. And finally the command, which is clear and start OpenOCD-F board/your config file and exit. When you try the debugger for the first time, you might have noticed that Visual Studio Code doesn't always start the debugging properly, or it stops unexpectedly. This is very annoying and makes the debugging process very fragile and frustrating. To solve this, we need to add this flag here, to tell OpenOCD that you are not going to debug a multi-threaded application, even if you are running FreeRTOS. This is a very important step. The reason is that, if you don't add that flag, OpenOCD is going to debug all tasks at the same time, and eventually, Visual Studio Code can lose track of one of the threads, giving error or not even start debugging. Even if our application is multi-threaded, most of the time, we are interested in debugging only the task that hits the breakpoint. So it's okay to have this flag set, to have a better debugging experience. But feel free to try yourself with and without the flag to see the difference in performance. Now, in the launch.json file, let's add this line, pre-launch task, pre-run. This will call our VS Code task every time we start the debugging session. Now, every time we start debugging, it will open an external terminal running OpenOCD automatically for us. Let's now automate the loading of the firmware for us as well. One of the cool things about using a debugger is that we can load the firmware straight from it. That way we don't need to use this USB cable to load the firmware anymore. First of all, we need to tell the GDB debugger how the memory in our project is structured inside our ESP32, so we can load the binaries in the proper memory positions. For our simple Blink example, the memory structure looks like this. The bootloader, which is responsible for loading our application, has 28 kilobytes reserved to itself and starts at address 1000. Followed by the partition table, where the definition of our partitions are, which starts at address 8000 and can go up to 4 kilobytes. And finally, our main application goes from here onwards. Since we haven't changed this project's configuration, we have only 2 MB of free space to use. We'll get into more details in the next video. To find the addresses for our project, we can just run the command idf.py build. Remember that huge command line from the first video? It is there where we can see the name of our binaries and their memory addresses. They can vary depending how you structure project. The way we specify those addresses to GDB is by adding them to the end of the debugger configuration. We'll need to add a new GDB command, mount-program ESP. With this command, we can load a particular binary to a specific memory address. For example, to write to the bootloader on this memory address, we have to type mount-program ESP, the bootloader bin file, the memory address 1000, and verify, which is used to check if the file was written correctly. And then we do the same for the other binaries. Partition table.bin at address 8000, and the main firmware blink.bin at address 10,000. And then monitor reset halt and flush writes. Okay, let's save. Now, when you click on debug, everything is taken care of. The firmware is going to be loaded, OpenOCD is going to connect, and we can start debugging. How good is that? Now, let's take a quick look in a simple debugging example. This is a very basic program just to illustrate how you can use an external debugger. I have a button connected to my I/O pin 4, which will generate an external interruption every time that I press it. This program just basically doubles the last number shown. You start with 1, 1 becomes 2, 2 becomes 4, 8, 16, and so on. Look how strange it is. It turns to 0 when it goes above 128. As we are using an external interruption, we are not able to print some information at this point because this code is being executed by interruption. Let's use our debugger to figure out what's wrong with our code. Let's add a breakpoint here and stop the execution of our code right when you double the counter. When the breakpoint is hit inside this method, we can see the value of the counter variable before we apply the double operation. The counter variable holds 1, and pressing the step over button on the debug bar up here, we can jump to the next line and check the counter variable again. Now we can see the variable holds 2. Also, we can even use step in if you want to see what hardware instance milliseconds does. And also step out if you want to see what's calling that callback function. For a overview, we can check here the call stack with the function history. We can see the counter is performing the math operation properly, and we know that our bug is a number after 128. So let's put a conditional breakpoint here to stop the program only when the counter is 128, like this. So let's hit the button and there we go. Our breakpoint stopped only when our expression was satisfied. Let's jump over and see what the counter variable has. It is correct, but somehow when you return the counter value, it's not returning the right information. Can you see why? The function getCounter returns a uint8. It means that this function will return an 8-bit variable, a byte. But if you take a closer look at the counter variable, it is a 32-bit variable, 4 bytes. Every time we apply the double operation, we shift the value 1 bit to the left. When that happens for the 8th time, our number will be bigger than 8 bits. And since the getCounter can only return 8-bit numbers, it ends up returning 0. We can fix it by changing the type of my method to return the same type as my variable. After recompiling and load the fixed firmware version, we can see now that when we press the button, the program performs the calculation properly and shows the correct number in the display. That was a simple but common mistake that many programmers do. Thanks to our debugger, I was able to freeze the flow of my program inside an interruption and have an overview of all my variables, going straight to the problem. As you can see, having an external debugger is very useful and helpful for firmware developing. Before I go, let me know in the comments if you like this type of content and what other topics you want to learn about. Don't forget to like and subscribe if you don't want to miss my next ESP32 videos. See you in the next one.